So hello everyone, welcome back to the YouTube channel Devotion of Knowledge. Once again, today we are back again with a video on cycle detection. But in the previous video, we did cycle detection using depth first search approach, and in this time we are going to use breadth first search approach. See, the main difference between both the approaches is this one is recursive, this one is iterative. Well, the approach is somewhat similar in both the ways. We will see how we will be detecting cycle in the graph. And yes, please make sure the graph will be undirected using breadth first search in this video. Okay. So here we are given a graph, undirected graph, as you can see. And as per the norms and protocols, we have to use the data structure Q in breadth first search approach. Okay, so we will be using Q data structure. Okay, yes, Q data structure. And yes, let's understand how we will be approaching the problem. Yes, recording is still going on. Okay, so as we all know, we will be starting from the first node and we will be inserting this node into the queue with 1 and -1. We will understand why we have inserted -1. Now, what are the, and we will also make visited 1, and yes, visited array is must in any problem of the graph data structure. Okay, so we will mark 1 here because it is visited. Now, what are the adjacent elements of 1, 2 and 3? Okay guys, first of all let us make a adjacency list. 2, 3, 2 is connected to 1 and 4, 3 is connected to 1 and 5, 4 is connected to 2 and 6, 5 is connected to 3, 7 and 6, 6 is connected to 4 and 5, and 7 is connected to only 5. Okay, this is our adjacency list that we are having. Now, adjacent elements in the list of 1 are 2 and 3. Okay, so we will be inserting 2 and 3, but along with the 1, because 2 and 3 are children of 1, because we are going to 2 and 3 from the parent, which is 1 in this case. So in Q data structure we will be maintaining node as well as its parent. Okay, we will mark 2 and 3 as visited. Okay, now what are the elements in the adjacency list of 2? It is 1 and it is 4, but we won't be considering 1 because we have came to the 2 from 1 itself. So 1 is a parent of 2, so we won't be considering 1. So we will traverse from 2 to directly 4. So, and yes, we will be popping out each and every element as soon as we reach there. Okay, so we will be popping out 2, 2, from 1 we have reached 2, and from 2 we can reach 4 and 1, but we have reached 2 from 1, so we won't be considering 1, so we will be considering 4. So we will be inserting 4 comma 2 because 2 is the parent of 4. Okay, now which is the next element? Wait a second, this got erased. Okay, perfection is important. Okay, yes. Now another element in the queue is 3 comma 1, so we will be writing 3. We have reached 3 from 1, and what are the elements in the adjacency list of 3? It's 1 and 5, but we won't be reaching to 1 because we have already come to 1 from, because we have already came to 3 from 1. So now we will be inserting 5 into the list. So we will be writing 5 comma 3. Okay, and yes, I have forgot to update the visited array. It will be 1 for 4 and 5. Okay, now which is the next element? It is 4 comma 2. We will be popping out 4, parent of 4 is 2, and from 4 we can reach up to 2 and 6, but 2 is parent of 4, so we won't be considering it, and we will be reaching to directly 6. So we will be marking 6 as visited in 1, and we will be inserting 6 comma 4 here. Okay, see, now we were here, we have traversed up to here, to here. Now which is the next element? 5 comma 3. Let us erase all this stuff. Okay, next element is 5 comma 3, so we will pop it out. 5, parent is 3. Okay, now there are 3 elements, 3, 7 and 6 in the adjacency list of 5, but we won't be considering 3 because it is a parent of 5. Okay, now 5, we will be reaching 7 first of all. Okay, we will be marking 7 as 1 and we will be inserting it 7 and the parent of 5. Now the main twist comes. Please focus. Now another element is 6, but it is already visited. See, another element from 5, 1 we can reach up to 7, we can reach up to 3, but we won't be considering it because it is the parent of 5, and another element is 6. But 6 is already visited. 6 is already visited, as we can see in the visited array. It means that someone before us has already reached 6 as this path, because 6 has been visited from 4 because 4 is the parent. So from this path 6 has been already visited. It means we are standing at this position, at this juncture, and we are trying to reach a node which is already visited from the peer present at the same level, because in breadth first search it is also known as level order traversal. So we will be iterating in the levels. So 6 has been already visited from some fellow node at my level, and I am trying to reach that node. How it's possible? It is only possible when cycle is present. I hope it is clear to you. Let me repeat again. See, we were standing on this node and we traverse from this node up to this node. We were standing on this point and we traverse into the levels, like first one, this one, then this one, then this one. Now, from adjacent list of 4, we already visited 6. So 6 has been already visited, and while traversing from 5, we came to know that 6 has been already visited from some other node, and I am trying to reach that node, and it is not even a parent of my node. 6 is not a parent of 5. It means that someone has already visited that node, and from another path I am trying to reach that node. What does this mean? What does this denote? Simple. Presence of cycle. I hope it is clear to you. We are trying to reach the particular node which has been already visited from some fellow node at my same level. It means only one thing, that cycle is present in the graph. Simple. Algorithm is done. Question is solved. Let us understand. We will understand time complexity and space complexity at the end of the video. But first of all, let us write the code for this one. Here we have to maintain a queue data structure with a node and a parent along with node present, because we have to make sure that we are visiting a node which is already visited along with not being a parent of that node, like this. Okay, so let us head straight to write the code. Yes, recording is still going on. Okay. Yes, and also there can be a possibility of having connected components, as it is shown here. Yes, here connected components can also be present like this. Here it is completely a one section, it is completely another section. We will also take care of those connected components if present, because if you have seen my previous video, we have done this by passing -1 as the parent. We will see here how we will be doing it. So first of all, we will have to initialize a vector of int visited array, which is must in the problems of graph data structure. What will be its size? It will be equal to the vertices present, and initial we will be marking it as 0 because on the initial stage we have not reached or we have not visited any node. Okay, and now see, we don't know that whether connected components are present or not. For example, graph is like this. Here, in this section, there is not any cycle present. Even in this section, there is not any cycle present. But cycle is present in this component. So by initializing breadth first search here, we will be able to iterate only in this part. We won't be able to go up to this part and go up to this part. So we have to call breadth first search for each and every node which is not visited, because here this 3 will be visited but this all won't be visited. So even after initializing, after going BFS to this 2, still this will be remaining. So we have to call BFS for each and every node which is not visited. Okay, so if visited of I is 0 means not it will be 1, then we will be calling boolean b equal to BFS of uh, visited adjacency list and the node at which we are standing. Okay, let us write the function boolean BFS, because return values we have set as boolean. We can also have int, but in that case we have to return either 0 or 1. Okay, boolean BFS will be taking vector int of visited as input as a parameter, vector of vectors as adjacency list, and int node. What will be your first task? We'll mark that particular node as visited equal to 1. Okay, now we have to initialize a queue data structure as integer q. Yeah, and as I told you, when we are standing on the first one, for example here, this node won't be having any parent. So for the first node we have to pass some dummy parent. So let us pass -1, because there is possibility to come 0 as a value in the graph. Not in this one, but if you are trying some problem or similar logic in some different problem, there is a possibility to come 0 as a node. So it will be more convenient for us to pass -1 or in negative value as a parent. So we will be passing q dot push. What is our node? It is node and initial parent is -1. Okay. Now we will write the main logic of BFS. We will be iterating through the queue for how much times? Till the queue is not empty. Okay. Int node equal to queue dot front dot first, int parent equal to queue dot front dot second, because we inserted node in the queue in form of first element is node and second element is the parent, and after getting it we have to pop the queue. Okay, now we will be iterating through the adjacency list of the node for adjacent node, auto adjacent node into the adjacency list of node. Okay, if that particular element is not visited, if that particular element is not visited, we will make it visited, visited of adjacent node equal to 1, and we will be pushing that particular element into the queue. Q dot push adj node, and from where it has been visited? From the parent, which is node itself. Simple. Now comes the main thing. What if the node is already visited? Then it has to be the parent. It has to be the parent. So if adj node is not equal to Parent means if it's already visited and it is not even the parent of that, then we will return true because we have reached this particular node which is already visited and it is not even a parent of 5. Yes, so we will return true because cycle is present. And if all those conditions iterate are iterated satisfactory without any problem, it means cycle is not present in that particular component if connected components are present. So we will just return false in this case. Now, as we have called B for that particular component, if B means if it is true, then we will return true. Else, after making sure that each and every part has been visited, each and every component has been taken care of, no problem is there, then we will return false in this case. Simple. Let us run the code. I less than V. Okay, the parentheses are not being handled perfectly. Okay, code is running without any error. So let us submit it and see if there is any kind of error or not. Okay, done. Yes, test cases are passed successfully. Now let us understand the time complexity. See, the one for loop we are running for each and every node or each and every vertices. So first of all, we have to consider of capital V for each and every node because we are going to each and every vertex and checking whether it is visited or not. Okay. And now for each vertex, for example, in worst case, every adjacent element is being called. Every adjacent element is being called. So if we make total of all this, if we make total of all these adjacent elements present of each and every vertex, it will be equal to twice the edge. Okay, let's count. How many edges are present? 1, 2, 3, 4, 5, 6, and 7. Count, there will be 14 elements present. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It is equal to always twice the edge because each edge corresponds to 2. From A to B, we will be also pushing A in the adjacency list of B and B in the adjacency list of A as well. So it will be, in worst case, we will be iterating through all these edges, all these nodes, which is equal to twice the edges. So twice the edges. But when we are considering worst case, we are not considering a constant. So it will be O of V plus E, which is the same as DFS as well as BFS. Space complexity, it will be O of V simply because we have not taken any extra space apart from visited vector V, and also this Q dot means Q data structure, and also in worst case it will max to max occupy number of vertices only. So it will be O of V plus V, O of V twice. But as I told you, we are not generally considering any constant, so it will be O of V at the end of the day. Okay guys, so I think cycle detection using level order traversal, or you can say breadth first search, BFS, is clear to you. Time complexity as well as space complexity we have also considered. We have also written a code from scratch, and if any doubt, any confusion, please make sure you are writing the comments, and please make sure you follow the channel for more related content and related videos if you find the channel interesting. Otherwise there is no question of following the channel at all. So here we conclude. Cycle detection is over in undirected graphs. If you guys want, please comment. We will be also making the videos for directed graph as well. And please don't worry if you are aware about undirected graph. Directed graph is just a pinch of salt to understand because it is very easy and there is not any hi-fi or rocket science involved in it. We are just supposed to maintain a vector or data structure which contains the path on which we are traversing. So I hope this video is over, and all the content that I was supposed to deliver has been delivered successfully. We will meet in the next video. Till then, please keep learning, please keep exploring. We will meet in the next video. Till then, goodbye.